Good morning, everyone. My name is Slobodan Simonovic, and I am coming from the University of Exeter, Ontario, which is located in London, Canada. I will be talking this morning about the systems approach to modeling water, energy, food nexus. Before I start, I would like to thank you for the opportunity to share this research experience with you and apologize for not being able to be in person with you. Definitely my loss. Next slide, please. I'll start with the conclusions of my presentation. Water, energy, food nexus is imposing new challenges to research and modeling. These challenges are originating in a very high level of integration between the nexus components, very high level of complexity of each of the components, and the set of common concerns they share. In this lecture, I will be making a case for use of systems approach to model the water, energy, food nexus. And in particular, the implementation of system dynamic simulation is an appropriate tool to capture the complex structure of the three components and interactions between the components that lead to the behavior of the system. Through our case study, we demonstrate that successful implementation of system approach in modeling water, energy, food nexus on global and regional scales, and I think with confidence we can extrapolate that the same approach will be of value for modeling on any other scale. ANEMI model example is a model of society-biosphere-climate system is selected to demonstrate the advantages of system dynamic simulation and also ability to model the water, energy, food nexus in the holistic way. Next slide. My presentation will start with elaboration of challenges that are coming from this new old context, a discussion of integration, introduction of systems approach, and then focus on the presentation of ANEMI model examples with possible elaboration of some lessons learned in the process. At the end of the lecture, I will repeat my conclusions. Next slide, please. What is the definition of nexus? It's defined as a center point of something or center of various connections. That term that very well fits with the joint consideration of water, energy, and food as the three key pillars of the global security, prosperity, and equity. We have to note that the current approach to questions related to water, energy, and food are mostly focusing on these systems independently. And that comes from the kind of different perspectives that we may take. If you're within the water resources management field, you look at the food and energy systems as users of the resource. If you are within the food production system, you are looking water and energy as inputs. If you are in energy area, you're looking water as input and food as the output. So these different perspectives are artificially dividing the sectors and pushing policy and regulations to arrive at suboptimal solutions. Another possible reason is that each of these areas is very large, very complex area in itself. So that leads to the set of challenges that we need to consider in order to look at them together. Next slide, please. What are the challenges? The common concerns that are present in water, energy, and food sectors are access to services, environmental impacts, and price volatility. Also, we have a fact that all three different areas are driven by two key drivers. On one side, growing population, from all the questions from poverty to population health, and on the other side, climatic change, where the different approaches being discussed in dealing with the climate change are bringing out the importance of one or more of the sectors of our interest. When we are talking about mitigation, usually the energy is being emphasized as the place where the solutions are, or when we are talking about adaptation to climate change, land use and use of water is coming into the picture. The fact is that there are enormous opportunities for higher efficiency if we put and consider these three areas together. So studying them in a holistic way and increasing our understanding of interactions between different components of the nexus is one of the prerequisites for much more efficient management of it. At the end, we all agree possibly that it is all about the feedbacks. I apologize. Before I proceed, let me kind of emphasize once more by sharing some numbers that I'm fully aware you've seen that illustrate the scale of the problem. 1.4 billion people without access to electricity, 3 billion people without access to modern fuels and technologies for cooking and heating, 900 million people without access to safe drinking water, 2.6 billion people without sanitation, 900 million people chronically hungry, and about 2 billion people lacking food security. These are impressive figures that are calling for serious attention of the world. What are the possible ways to deal with the seriousness of the problem? Next slide, please. One of the ways is to consider all these three areas together. In order to consider them together, we need a different view. Systems view is definitely available for consideration of complex systems and implementation of this kind of holistic approach, but still demonstrating some difficulties in translating the systems view outputs into government policy decision-making processes. Systems view is very efficient with dealing with system structures, with dealing with interactions between system elements, and generating the kind of behavior of the system over time. Next slide, please. That leads me to our example. In this particular example, with the support of the National Natural Sciences and Engineering Research Council, through two different research grants, we proceeded with the development of the system dynamics-based model of society-biosphere-climate system. That's named ANEMI after the Greek name for the four winds, heralds of the four seasons. Over the period of 6 years, we were working on the development of the model in order to provide support for the communication between science and policy, and also examining the effects of climate change on the socioeconomic and environmental sustainability. We were able to assemble a real interdisciplinary team under my leadership that included a number of people from engineering with a systems modeling background, people from social sciences with background in geography, political sciences, economics, people from natural sciences with background in physics and climatology. We also had a great opportunity to work with 5 federal government departments as real research partners throughout this period. Environment Canada, Natural Resources Canada, Department of Finance, Department of Fisheries and Oceans, and Department of Agriculture played a very important role in this research process. Next slide, please. And here is how the process proceeded. We divided the whole process into kind of 3 different phases. In the first phase, the focus was on selecting appropriate methodological approach, and that led to the selection of the systems approach and implementation of the approach through the system dynamic simulation. These methodological issues were discussed with the partners during the first workshop, and the final choice was made that led us into the second phase, where the model development was done through the establishment of the structures, selection of the sectors, and preliminary simulations that were helping our partners understand better the benefits and advantages of the approach, and also help them articulate the key issues and concerns that were then used in the development of the simulation scenarios for the final model implementation. The second workshop was used after the completion of the model to convey some of the model structure questions to the partners and also reconfirm what are the key issues and how are we going to put these key issues in the simulation scenarios and use them for the final analysis. In the third phase, model was expanded with the very serious economy energy sector, and a regionalization of the model was done in order to assist our partners in policy making within the region of Canada. Model was used through the scenario analysis and identification of model advantages and disadvantages. That led us to a final workshop where the model transfer was performed and model was shared with our partners, and future work was identified, or topics for the future work were identified. Let me now start talking a little bit about the model. Next slide, please. This is a very generic presentation of the model structure. It is a so-called integrated assessment model that includes 9 different sectors built around the backbone of the water, energy, food nexus. These 9 sectors include carbon cycle, climate, water use, water quality, surface flow, population, land use, food production, and energy economy sectors. They are all of very high level of complexity based on the current knowledge in particular field. Please hit enter once more. As you will see, the most of the sectors fit into the structure that describes the water, energy, food nexus. Water demand, quality, and surface water covering the area of water. Energy economy sector covering the energy, land use and food production covering the area of food. The 2 drivers that I mentioned at the beginning of my presentation are basically captured with the remaining 3 sectors. Climate and carbon are describing the processes related to climatic change that affect each of these 3 nexus components. And on the other side, the population sector is also incorporated, that affects the elements of the nexus. Each of these 9 model sectors is of pretty high level of complexity. Next slide, please. These 3 pictures are illustrating the so-called stock and flow diagrams of some of the model components, just to kind of show you how different state variables are connected through a set of flows, and basically feedback relationships or feedback loops are established by linking them linking these components throughout the structure. The picture on the top is showing one element of the water sector, the picture in the middle is showing one element of the food sector, and the kind of simplified diagram is showing a very complex structure of the energy sector. Behind these so-called object-oriented diagrams that include the stocks and flows, we have a very detailed mathematical representation of the model. Next slide, please. Just as an illustration, I selected the mathematical description of one of the water sectors, available water resources, that is represented with 2 stocks of oceans and land surface, and number of different flows from evaporation, evapotranspiration to precipitation, melt, percolation, and ocean runoff. All these equations are representing actually the state variables and flows that are forming the structure of this model sector. Each of 9 sectors is equally complex, and this is not the complete actually representation of the water sector. Therefore, you realize, in spite of the very simple graphical presentation of the model contains pretty high level of detail. We have about 600 state variables, about over 2,000 equations, and what is much more important, through this structure we were able to assemble close to 8,000 various feedback relationships that are basically driving the dynamics of such a complex system. Next slide, please. One of the very important innovations incorporated in this model is use of optimization and simulation simultaneously, side by side, in the energy economy sector. The price of fuel and the capital stocks for energy production are simulated based on the optimal value of GDP, energy production, and energy use across different sectors. The optimal value of these components are driven by the optimization scheme in relationship to the population and climate sectors as the key drivers. Next slide, please. We also developed two versions of the model. One that functions on a global scale and look at the whole world as a unit. And the second version that is looking at Canada as in one region and the rest of the world as another region. This regionalization was of essential importance to our partners in order to support the policy making on the national level. However, in modeling answering the modeling questions related to regionalization, we realized that the number of sectors that are actually occurring and functioning on a global scale and cannot be regionalized, like carbon, climate, hydrologic cycle, and remaining sectors being capable of representing the difference between different regions. Food, energy, land use, water demand, population, and water quality differ for Canada as a region and the rest of the world. This is the kind of template that can be used in further level of detail in the development or further regionalization of the model or implementation of the similar modeling approach to various modeling scales. Next slide, please. The final stage on model development incorporated actually policy scenarios, development of the policy scenarios, and that process of policy communication was a very important part of our research. It was conducted through various forms of interviews, direct interviews of the partners, identification of the policy questions by the research team, and finally the conversion of the issues expressed by our partners in the form of the simulation scenarios that can be then analyzed with the use of the ANEMI model. We started with the initial set of scenarios that included about 8 different scenarios: carbon pricing, economic growth rate, water pricing, North American water stress, irrigation, energy subsidies and pricing, land use, and so on. At the end, after the second workshop, we all agreed that all these different questions and issues can be kind of addressed through the 3 integrated policy scenarios. One describes the implementation of the carbon tax. The second one that deals with the increase in the water use. And the third one that deals with the increase in the food production. The remaining slides will show some of the results of the implementation of the ANEMI model in the analysis of these 3 different scenarios. This is a set of slides arbitrarily selected for outputs to illustrate the use of the carbon tax scenario. In this scenario, we utilize the linear ramp tax for industrial emissions, starting with $10 per ton of CO2 in 2012, rising to $275 in 2100. And we also added on top the carbon capture for coal of $75 per ton. As you can see, the baseline runs are represented using the dashed line, and the simulation of the particular scenario, in this case with the carbon tax scenario, is depicted here with the red line. The model demonstrated considerable response to the introduction of the carbon tax. The GDP was higher with the tax. The energy used for electricity production dropped with the introduction of the tax. The atmospheric CO2 concentration was majorly under control with the introduction of the tax. And at the end, there were some consequences on the population and other sectors. Similar graphs can be generated from almost every sector of the model, and multiple conclusions can be drawn from the runs under this particular scenario. Next slide, please. This slide shows some of the results of the implementation of the second scenario. In this scenario, we looked into kind of integral increase in the water use of arbitrarily selected 15% to just evaluate the response of the model to the potential increase in the water use. As you will see from the selected outputs, again the baseline is shown as a dashed line, and the scenario run is shown with the use of the red line. By increasing the water use, the available surface water is dropping, the water stress is increasing, food production is responding for some minor decrease, and global population too, which requires much more detailed understanding of what is happening through the water component of the Nexus and the model, where the water quantity is directly related and affects the water quality, and the water quality then propagates, or decrease in water quality propagates into the sectors of food production and population growth. Next slide, please. And my last example is showing some of the results from the third implementation of the third scenario, increased food production scenario. We represented the increased food production through the basically change or increase in the land conversion from forest to agriculture. And as you can see, the model responded again with in a particular way by increasing the land for agriculture. We demonstrated a decrease in the available surface water, some increase in the atmospheric CO2 concentration, and some minor impact on the food production over the long term. I hope that these examples are illustrating or giving you some feeling what type of questions and answers can be obtained through the implementation of the systems approach, in this case system dynamic simulation, and selection of number of simulation scenarios. Next slide, please. That brings me back to my conclusions that water energy food nexus is imposing new challenges to research and modeling. They're coming from high level of integration of the nexus components, high level of complexity of components, and number of common concerns that they share. I think we made a pretty strong case for the implementation of systems approach in modeling the water energy food nexus, and also illustrated some advantages in using system dynamic simulation in the process. Our modeling was done on a global and regional scales, and I think there are no limitations for using the same approach in conducting modeling of the water energy food nexus on other scales. ANEMI model example is, I think, an excellent example how the nexus can be modeled in integrated way, with the two drivers represented with the remaining sectors of our model. We were able to represent very high level of integrated performance of the model, as well as understand better the relationships between the model components, nexus components, and consequences of different policy, and analyze the consequences of different policy options. Next slide, please. I would like to thank you very much for your attention. Hope that I didn't take too much of your time. For those of you who may be interested in a little bit more details about my presentation, here is the list of some of the most important publications. They all can be obtained by following the link at the bottom of this slide. Thank you very much. I will be available to answer some of your questions in person tomorrow morning. Goodbye.